Assalamu alaikum and good morning. Okay, so today we are looking at the section 15.2, which is about double integrals over general regions. If you would remember that from the last lecture, the region we looked into was rectangular region. So that was the double integrals over rectangular regions. And here the region can be different from rectangular. So it's a more generic region we are looking into, over which we are considering the double integrals. And it will be the double integrals over bounded non-rectangular regions. So when I say bounded, it means that we are not considering regions for instance, in XY plane, which are infinite in extent. So these will be bounded regions. You say they are finite bounded regions and over non-rectangular with the non-rectangular boundaries. So as before, what we do is to partition the region into a number of rectangles in the same way that we did before. So for instance, if you remember that in the last lecture, what we did was to partition a rectangular region. Here the region is different. You see, it's a region is non-rectangular, over which we are trying to find finding the double integrals. Okay, so this is non-rectangular region we are considering. And before, in the last lecture, we considered rectangular region, and we partition the rectangular region into these small, you can say, rectangular grid. So this is rectangular grid is consisting of a large number of small rectangles. Okay, so the partitioning is similar as before, but only the boundaries of this region is different from the previous case. So what you do is that we number these rectangles of the partition which we have introduced. We number these rectangles in some order from 1 to n, and let delta AK be the area of the kth rectangle. So we are numbering those small rectangles from 1 to n, and then calling, for instance, delta AK be the area of the kth rectangle. Okay, so if you refer back, so this is, for instance, the kth rectangle here. And so we have numbered all of these small rectangles which are inside this region. And for instance, this is the kth rectangle whose middle point is this one, xk, yk. So this is the point with the coordinates xk, yk. And considering that this region is located in the xy plane. Okay, we then choose the point xk, yk in the kth rectangle and form the Riemann sum. So the Riemann sum is formed in this exactly the same way here as before. So this is our Riemann sum, consisting of making the product of the function, value of the function at the middle point of that small rectangle, multiplied it by the area of the small rectangle, which is delta AK. So this kth rectangle, if you multiply the area of that kth rectangle, which is here, multiplied with the value of the function at the middle point of the kth rectangle, okay, and then you add such products for all the small rectangles. So because you have numbered these rectangles by the subscript k. So you are forming this infinite sum, or well, it is a finite here when n is finite, and after that we apply the limit when n goes to infinity, then it becomes an infinite sum. So this is the Riemann sum we are looking into. So essentially, it is the same expression as before, which we consider for the rectangular region, but the difference is the region is different. The boundaries of the region are different. So let's make it a bit smaller. So this is the rectangular grid partitioning a bounded non-rectangular region into rectangular cell. So this is our grid, which is partitioning this non-rectangular region, which is here, and it is partitioning into rectangular cells here. Okay, now let's say bigger. Now, as you know, that what was the norm which we introduced in the last lecture? Norm was the maximum height or the width of those small rectangles in the partitioning. So for instance, refer back to here. Norm, as we defined in the last lecture, was the, if for instance, this is all the partitioning we have introduced. So norm is the maximum height or the width of these small rectangles. And we use the concept of the norm here again, and it is saying that let us so the norm of the partition forming Sn, which is the Riemann sum, if it goes to 0, so if norm goes to 0, it means the maximum height or the width of the small little rectangles, they go to 0. Or if that happens, it means the number of rectangles goes to infinity. So here is the norm is going to 0. The width and the height of each enclosed rectangle goes to 0, and their number goes to infinity. Number goes to infinity because if the width and the height of the if the width or height of the maximum size of those rectangle goes to 0, it means you need to introduce an infinite number of small rectangles to cover the area. And if f of xy is a continuous function which you are looking into, so then these Riemann sums converge to a limiting value and not depending on any of the choices we make. So it is essentially saying that it is irrespective of which choices you make in introducing the partitioning. Irrespective of that, the Riemann sum is going to converge to the same limit if the function is a continuous function. And this limit is called the double integral of the function of two variables over the region, which is a non-rectangular region we are having. So this is how we define the double integral. Is here. This is the Riemann sum which we are having. Okay, so it is Riemann sum with the limit, the partitioning or the partition. Sorry, this is norm of the partition going to 0. So this converges to a limit. When this happens, when the norm approaches to 0, this converges to the double integral of the function f of xy over the region R, which is non-rectangular. So how do we calculate the volumes in this case? So of course the volume will be the volume over the non-rectangular regions in the xy plane. So here we are having the situation like this here. So previously it was a rectangular region in the xy plane. So here we are having a region like this, about you can say an ellipse or a circle in the xy plane. And this is the function here. So z is equal to f of xy. Okay, so this is a surface in 3 dimensions. So over some region in the XY plane which is non-rectangular. So this is a situation we are looking into. So if f of xy is positive and continuous over R, over this region R in the xy plane, so the function is continuous and positive, we define the volume of the solid region between R and the surface, which is z is equal to f of xy, to be given by this double integral. So the region, the solid region we are looking into is this one. So you can say this is the solid object in 3 dimensions whose uh, this end, it is confined between the region in the xy plane, which is here somewhere, okay, and from the above, which is bounded by a three-dimensional surface, which is here. Okay, so it is a three-dimensional surface constructed over this region in the xy plane. And now we define the volume of the solid with the curved base as the limit of the approximating rectangular boxes. So how this is happens? So it's just a second. So here, so the region in the xy plane is being again divided into small rectangular partitioning or small rectangles, and for each little rectangle, like here in this case, whose middle point is xk and yk, and this rectangle is the kth rectangle. So here, for instance, the value of the function is represented by the height of this dotted line here, connecting the red point with the blue point. Okay, so what you do is you calculate the volume of this, you can say this object here, by multiplying the height with this small area of this small rectangle here. And the area is delta AK, and you multiply it with together, and this gives you the volume of this object here. Okay, and this is the object, and when you collect together all these such volumes over all the region in the xy plane, and this gives you, in the limiting case, when the norm of the partition goes to 0, okay, in the limiting case, in that case, this limit, it approaches to the double integral of the function of two variable, which is calculated over this non-rectangular region. So the volume of the solid with the curved basis, so the solids with the curved basis, so the curved basis here, the wording here is referring to the curved basis of the region in the xy plane. So if a region is like the one shown in the figure 15.10, so this is 15.9 and referring back to here, okay. So this is our figure 15.10. So this is a region we are looking into. Region R is a region which is bounded above and below by the curves y is equal to g2 of x and y is equal to g1 of x. So let's look at this region. So for instance here, so here this is the xy plane you are looking into, and if I make it a bit bigger, you say that the region here is bounded by this curve and this straight line and this curve here in the xy plane. So these both curves are located in the xy plane, and this curve is y is equal to g1x, whereas this curve is y is equal to g2x. And this line here is x is equal to a. So the region is bounded above by y is equal to g2x here, and bounded below by y is equal to g1x by this line. Okay, and On the one side, the region is bounded by a line which is x is equal to a, which is this dotted line. And the other side is bounded by this line, x is equal to b, which is this solid line, okay? So you are considering the volume of this object, three-dimensional object, and this surface over the top of this object, so bounded by this top here, this top surface. Of course, it is describes the value of the two variable function. So it is here, z is equal to f of xy. So here, if the region is like the one shown here, which is bounded below and above by these curves, and on the sides by the line, these are the two lines, x is equal to a, x is equal to b. Then we can calculate the volume of this object by the method of slicing, which what the method of slicing it consists of. It calculates the cross-sectional area. So here the AX is a cross-sectional area, and let's look at it. Have a look at it. So this is the, for instance, if you have got a plane which is running parallel to YZ plane and it is located at X, at the coordinate X here, so the plane here, okay, and it, when it cross-sects this solid object, it cross-sects this area, this blue one, the cross-sectional area, okay? And remember that this cross-sectional area from the top, it is bounded by the value of the function here, and this this is the vertical line which is parallel to the z-axis, and here this is another vertical line parallel to the z-axis, and here this line is of course x is equal to, well, this is just the defined by the coordinate x, a this line, okay, in the xy plane. So we need to now calculate this area which is ax, this blue area, and to calculate this blue area, cross-sectional area here. So how do we calculate this cross-sectional area? It is to integrate this function f of xy with respect to y. When you are integrating with respect to y, you are treating x as constant. So this is exactly what is happening. When you are calculating this area, of course, the x remains constant. So x remains constant, so you are considering this plane running through the solid object and with the coordinate x, okay, and it is parallel to yz plane. So here x is constant. So to calculate this area, what you do, you have got this height, this dotted line height, multiply it with this height, multiply the height with the incremental small change, which you call dy along this direction, okay? So this gives you a small strip of the area. So value of the function multiplied with a small change in the y coordinate, which is called dy. So dy multiplied with f of xy, it gives you a small strip of this area, and then you have to integrate that with respect to y, whereas y is changing from this value of y here, what is given as g1x, and the value of y here is g2x. Okay, so remember that this is the value of the y is g1x here. Okay, so this is indicated by, because this is the curve which is y is equal to g1x. Okay, so here is the value of the y g1x, and here is the g2x. So you are having this strips, the vertical strips from this blue area. Each strip has got an area which is called f of xy multiplied with dy, okay, and you are adding those strips together and integrating from y is equal to g1x and y is equal to g2x. So it is here next, okay, now here. So this is the area ax. So you have got f of xy multiplied with dy. So, and this is the area of a small part of the blue, the cross-sectional area of blue, or this is a strip of that, okay? And then you integrate from y is equal to g1x and going to y is equal to g2x. And then if you have calculated this area, what you do in the next step is to multiply this area, this one, okay, with a small increment along the x-axis. And then, okay, if you increase small increment along the x-axis, it generates a small volume. So if you have that, then you integrate from x is equal to a to x is equal to b. So this is what's happening here. So here, so you multiplying this area ax, and of course you can see that this is a function of function of x only, because when you are integrating with respect to y, this two variable function, and you are applying your limits that y is changing from y is equal to g1x to y is equal to g2x. When you are applying these limits, you are eliminating the y in the resulting expression. So you are left with an expression which only involves which involves x only, dependence on x variable only. Okay, so this is the area of that, the cross-sectional area given as a function of x. So if that is the case, so now we need to integrate this area from x is equal to a to x is equal to b to get the volume as an iterated integral. So this is our area as a function of x. You multiplied it with dx, and when you multiply it with dx, what you have a small differential volume element. So here we have, so this is the blue area, the cross-sectional area ax. You multiply it with a little differential change in the x coordinate. So multiplied with dx, and you get a differential volume element, and then you integrate that with of course with you are integrating with respect to x from when the x is changing from x is equal to a to b. So this one gives you this integral. So integral of this function f of x y g limits g1x to g2x. So this is the what ax is, okay. So this middle integral here, this is the ax, and then integrating ax with respect to x when x is changing from a to b. Okay, so this is now the volume of this solid object which we are considering here. So we are integrating the cross-sectional area from x is equal to a to x is equal to b. And now, and similarly, if the region is, if the R is a region like the one shown in the previous figure, but which is bounded by the curves x is equal to h2y and x is equal to h1y. So here these, you see that these curves in the xy plane are defined differently. So x is defined as a dependent variable of the independent variable y. So y is considered as an independent variable here. So instead of the usual definition that y is a dependent variable and x is independent, here we are considering y to be independent variable and x is dependent variable. Still these two equations are defining two curves in the xy plane. And here the situation is represented like here. So here in the xy plane, the region is region R, which is a non-rectangular region we are looking into, and on the two sides, this region is bounded by these curves. So this one is x is equal to h to y. Okay, so this is the curve x is equal to h to y, okay, in the xy plane, and this is the curve which is x is equal to h1y. So this is the other curve, and On the other two sides, we have got the region R bounded by these straight lines. So this is the straight line y is equal to d, and this is another straight line y is equal to c. Okay, so this is the region bounded by on one side by these two, on the two side by these two straight lines and the curves here. Okay, and then this top surface is the value, represents the value of the two variable function. Okay, so if the region R is bounded by the curves which are given here, x is equal to x h2y and x is equal to h1y, and the lines y is equal to c and y is equal to d, so these are the two lines, then the volume is calculated by slicing, again using the same method, and using the iterated integral. Is volume is given by integrating this function of two variable f of x y. So here you can see that it is first integrating with respect to x here, and integrating from h1 to h2y, and then the resulting expression from here, you can see that it becomes a function of y only, this one, this middle integral, and then you integrate that function of y which with respect to y when y is changing from c to d. Okay, so this has got the same geometric interpretation as before. So if you look into this integral, it is again consists of first calculating the cross-sectional area, which is the middle expression. But the difference is this middle expression will represent the cross-sectional area but calculated in a different way, that this is a cross-sectional area which is a function of y, contrary to what was the case previously, which was a cross-sectional area function of x. Here is a function of y, and then you integrate this cross-sectional area with respect to y when you change y is equal to y from c to d. So if you look into that, so here you see that this cross-sectional area, this blue one, for this cross-sectional area y is fixed here. Okay, so y is fixed at this, okay, at this value. Okay, y is fixed. So because when y is fixed, it represents essentially the cross-sectional area which will be cut out by the plane running parallel to xyz plane and passing through this line. Okay, this dotted line. So here, and now this cross-sectional area, as you keep on moving this plane in this direction, will keep on changing, but this cross-sectional area, the blue one, will then become a function of y only. Okay, so this cross-sectional area is a function of y, and then you integrate that, or you multiply this area by a differential change along the y-axis. You mean, so it is a function of ay multiplied into dy, differential change in the y direction, and this gives you a differential volume element. Okay, and then integrate that from y is equal to c to y is equal to d to calculate the volume of this solid object. So remember that this object is built upwards from the base, which is located in the xy plane here, and the curves which are defining the bounds of this region are uh, located in such a way that on the two sides we have got the line, straight line y is equal to c, y is equal to d. On the other side, these are the curves defined by x as given as a function of h2y and x as a function of h1y. Okay, so this one, okay, so the solid volume of the solid is shown here is given by integrating AY, so this is the area, the cross-sectional area, blue one, and multiplying with the differential change in y, dy, and integrating from C to D. And now this AY is given by this expression in the middle part here in the, so it is the AY is given as h integral from h1y to h2y, and then integrating this two variable function with respect to x. Okay, and then integrating this AY from, this is the AY, this middle integral, integrating it from C to D with respect to y then. So this gives you the volume. And depending on how you define this region in the xy plane, both of these results generate the same outcome. Okay, so but there is a difference. There is a difference is that this region, how this region is defined, it in fact guides us to using whether we use, which integral we use, this one or the one previously. It means that the whether we have got the boundaries defined by uh, x is equal to h2y and x is equal to h1y, or the other functions which are in which y becomes a dependent function, dependent variable on independent variable x. So that is will be different situations. So let's look at the particular cases. So and before looking into particular cases, the theorem 2, which is the Fubini's theorem in a stronger form, and saying essentially the same thing which we have just discussed, and is saying that if this is a two variable function which is a continuous on a region R, and remember that this region is non-rectangular. If region R is defined by this restriction on the independent variable x, which is x is going from a to b, whereas y is going from g1x to g2x. And again, if you remember that in the rectangular region in the xy plane, there were numbers here, not g1x and g2x. If you remember the previous lecture. Okay, so here we have got y varying from g1x to g2x, where g1 and g2 are the continuous functions on this interval a and b. Then in that case, the double integral of this function of two variable over the region R is calculated by integrating f of xy from g1x to g2x. Okay, so considering that x is here, x is considered as a constant, okay, in the calculation of this middle integral, okay. So you integrate f of xy, the function of two variable, with respect to y, first considering x to be constant, and then resulting expression here becomes a function of x only, and this one is integrated with respect to x then, okay, when x is changing from a to b. And similarly, if the region R, which is again non-rectangular region, which is defined by these constraints here, so here the constraints are different relative. If you look at these two constraints, they are different. It's here the y is bounded between C and D, okay, and the x is bounded is in this range h1y and h2y, where h1y and h2y are the continuous function or defined on this interval. So here again the same thing. So this is the double integral of the function f of xy defined over the region R in the xy plane. So it is now here in the middle part. Here is the again the refers to the cross-sectional area, okay, in the middle part here, and then the boundaries of this region are defined such that when y is a considered constant in this one, in this calculation of this middle area, y is considered as constant, and then the function is integrated with respect to x, and the limits are h1y to h2y, and then resulting expression becomes a function of y, this one, middle one. Then you integrate that with respect to y with the limits on y being c to d. Okay, so this one is an example one. Calculate the volume of the prism whose base is the triangle in the xy plane bounded by x-axis and these two lines, y is equal to x and x is equal to 1, and whose top lies in this plane. So this is a plane, the top lies in this plane, whereas the region in the xy plane is defined by these conditions. So there are bounded by the x-axis and the line y is equal to x, okay, and x is equal to 1. So let's look at this is the region you are looking into the xy plane. So the x-axis, x is equal to 1, this line, and y is equal to x, okay, so this straight line. So the region is bounded by this triangle in the xy plane, and now we have to calculate the volume of this solid object whose lower end consists of this, or lower end or the base consists of this triangle in the xy plane. So here we have this triangle, the same triangle, this one, okay, is here. And now if you, this is the plane you are looking into, this is the plane, and this is the plane is defined by this condition, z is equal to f of xy 3 minus x minus y. So this is our plane, this slanting plane, okay. And now how do we calculate that? By integrating. So again, this can be divided into these vertical columns and then constructing the Riemann sum and adding them together. And now, so what we do here is explain very well here is it says that the prism with a solid base in the xy plane, the volume of the prism is defined as a double integral over the region R, which is a non-rectangular region, of course, in the xy plane, okay. And we can calculate, so here if you consider a vertical line, which is this line, okay, this reddish one. So here, and for a vertical line which is here, if you introduce that, then for this one, here is y coordinate is 0 and here the y coordinate is x, okay. So if you are looking into calculating this integral, yeah, what you do is you introduce here it is f of xy dy, so this middle integral, so y is changing from 0 to y is equal to x. You see that y is changing from using this vertical line, y is equal to 0 to y is equal to x. So this is what is happening. So these are our functions which you have defined in the defining the generic integral, which was y is equal to g1x and y is equal to y1 is equal to g1x and y2 is equal to g2x. So these are the specific cases. So y is equal to 0, this one, and y is equal to x. So these are the boundaries. Okay, so you then integrate this function of two variable treating x as a constant. Okay, you see that in the calculation. So x is a constant. Integrate this with respect to y when y is changing from y is equal to 0 to y is equal to x. And now this expression becomes a function of x only. And then after applying the limits, and then you integrate with respect to x from x is equal to 0 to 1 because x is changing from 0 to 1. So here in the previous one, so what you do is here, this is our function, yeah. So here is integration with respect to x. So this is the alternative way. So here is the alternative way is that you integrate it Okay, let's look at it here. So here, this way is that you have got this vertical line running from this reddish line here, running from x is equal to y here, and x is equal to 1 here, x is equal to 1. Okay, so it is here, it's x is equal to y because this is a line defining y is equal to x. Okay, so x is equal to y and x is equal to 1. And then you have got this vertical line, and you integrate this uh, 3 minus x minus y from when y is changing from 0 to x. As you can see here, how is changing from 0 to x. So in the first case, if you look at that, y is changing from, in this case, so the integral is y is changing from y is equal to 0 and y is equal to x. So here is what's the 0. So these are the two limits, so 0 to x. So integrating this expression from 0 to x, and then integrating from with respect to x from 0 to 1. So this is exactly what happens. So here, this is the middle expression. You integrate with respect to y first, applying the limit 0 to x. This is the, after the integration, you get this part, and then the resulting expression here, as you can see, it becomes a function of x. And then you integrate this one with respect to x when x is changing from 0 to 1. Because in this one, as you can see, that x is changing from 0 to 1 here. Okay, in this one, and then the same integral can also be calculated by introducing the boundaries of this region differently. So here in the second part, what is done is that this is the same function. Now the integration is done first with respect to x, so it means y is constant. So if you now look at the figure, when y is constant, so it represents this line. For this line, y is a constant, and but y is a constant, then x changing from x is equal to y, which is this point, and x is equal to 1 at this point. So here what we do is that you integrate this from value of x, which is y, and value of x, which is 1. Okay. And then first integrate this one, and then the resulting expression which comes is generated by this integral, which is a function of y only. Then you integrate that with respect to y when y is changing from 0 to 1, because y, as you can see in this triangular region, is varying from 0 to 1 here, because this is a point where where it is 1 1, the coordinate 1 1. So here, so this one is now generates integration of this one with respect to x. Limits are y to 1, and then you obtain this part here. Okay, and then applying the limits, which is x is equal to y and x is equal to 1, and then you have integrate with respect to y here. Okay, so here with respect to y, and it is from limits 0 to 1 here, and then this generates the same outcome as before. So this generates the volume, and but the calculation is different how you calculate this volume. Okay, so we stop here, and I want to know if you have got questions. Okay, so are there questions? No questions? Okay, then we stop the meeting, and we meet on Sunday.